All right, so hi everyone, welcome back. A very good evening to you all. Myself, Ayush Tripathi, and welcome you all to this post analysis discussion of the last weekly contest 208. So before starting the analysis, just write a quick +1 in the chat box if I am audible, and also tell me how many problems you were able to solve during the contest. And what I personally believe, all the problems were from easy to medium level, and all the four problems were doable. There is no prerequisite at all. For the first two problem, which was very easy, the second problem you need to know the basic of bitwise OR property and bitwise AND properties. For the third problem, which is based on a very standard problem, longest increasing subsequence, and the fourth one, which is based on observation and some hashing technique. So write a quick +1 as a confirmation so that we can start with the first problem. How to master DSA? Can you please tell what are the patterns to master? So basically, there is no a trick. All you need to just practice as many problems as you can. There is no alternative. Just go and learn some topic and try to practice 10 to 15 problem based on that particular topic. So just tell me in the chat box how many problem you were able to solve during the contest. Okay, what's your native language? So we're going to discuss the solution in C++ only, but during the explanation, we'll try to keep the things as much as possible language independent. So you don't have to worry about the implementation. Just listen to my explanation and try to implement it by your own. I solved all the problems. Okay, that's great, Rahul. So starting with the first problem, let me just share my screen. First contest for me, not an issue. So yes, this template seems good to me. Does the rating of GFG really matters? Yes, you can mention it on your resume or on your LinkedIn profile. Anyways, starting with the first problem, but before that, let me check if everything is okay from my end. We'll answer all your questions at the end. So as of now, let's just focus on this a problem discussion. So starting with the first problem, given an array ARR, and here you have to choose three distinct indices I, J, and K. Among all possible such a triplet, find the maximum value of the expression. And the size of the array is always greater than or equals to 3 and up to 10 power 5. The value of the element can be up to 5 into 10 power 5. And this is the value of expression, and you need to maximize the value of this expression. So let's see how we can solve this problem. So this was a cakewalk problem, I would say. All you need to draw is just a basic observation. So the value of the expression, let me write the value of the expression which we need to maximize. So it is absolute value of ARR of j minus ARR of I plus absolute value of ARR of k. So here we selected three indexes I, j, and k. So k minus j plus absolute value of k and I. So ARR of k minus ARR of I. Now if you have observed one thing, then this is nothing but the differences between the integers on a number line, because we have a term absolute, and we have to maximize this value, right? And in order to maximize this value, let's just think in terms of a number line. So let's consider this is our number line. So we want to keep the integer as far as possible, right? Because in that way we can maximize the absolute difference. So let's select the smallest element of the array as index I. So this will be my smallest element of the array as ARR of I, and the largest element of the array as ARR of k. Then what are the possibilities we have for ARR of j? So we may have a multiple possibility, but actually you can select any integer as ARR of j. Because now if you have noticed one thing, then let's call this as a d1. Let's call this a difference as a d1. This is actually the value of the third term of expression. This third term which I have written. Now if you have if you select ARR of j, let's say somewhere at here we have our element ARR of j. So now what are the other two values we are adding? So the other two values that we are adding is this one. Let's call this as a d2, and let's call this as d3. Now it is clearly visible that value of d1, it is equals to d2 plus a d3. If you shift the value of ARR of j on a right hand side, then d3 will decrease and d2 will increase, but their sum will be equals to d1 only, which is constant. If you shift this ARR of j to the left side, then d3 will increase and d2 will decrease, but still their sum will be equals to d1. So my overall answer would be nothing but a d1 plus a d2 plus a d3, and we all know d2 plus a d3, it is equals to d1. So can be written in this way. It is 2 into d1. So 2 into d1, and I can also write in this way. The absolute value of a maximum element of the array absolute difference of a maximum element of the array and the minimum element of the array. So yes, this is the complete solution for the first problem. Now I hope it is clear to everyone. Coming to the implementation. So just simply find the maximum element of the array, then find the minimum element of the array. So this will be ARR of I, and this one is nothing but ARR of k. Now this will be your answer. So simply return it. So here Naman is asking, it is given that I should be less than j and j should be less than k. So definitely this property is satisfied. So the size of the array, actually there's no such thing mentioned, but we can assume that I is less than j and j is less than k. But there's no such thing mentioned. So the size of the array is always greater than or equals to 3. So we select the minimum element as ARR of I and the maximum element as ARR of j. Then in between you can select any integer for ARR of j, because all the values of ARR of j will give you the same answer. The time complexity will be order of n. This maximum element function will take a linear time, and minimum element function will also take a linear time. You can implement it by your own. Just simply run a loop, find the maximum element, run a loop, find the minimum element. Now coming to the next problem. Possible value of k. So before that, everyone write a +1 if it is if the first problem was clear to you. I just need a confirmation from you all. +1 if it is clear to you, so that we can discuss the second problem. So in the second problem, which is named as the possible value of x, so you will be given three integers a, b, and c. You need to find the minimum non-negative integer x such that a or x and b or x equals to c. And if no such x exists, then we have to return -1. And in order to solve this problem, you need to know the basic property of a bitwise. That's enough to solve this problem. So let's see. So the value of expression, basically a or x, then we take and with a b or x, and this value must be equals to c, right? And we need to find the minimum value of x. We need to minimize the value of x. Now let's see how we can solve this problem. So let's say we have a integer c whose binary representation is like this, some leading 0. So this will be a completely a greedy idea. We iterate over the bits from left to right, and if you consider 29 bits, the first 29 bits from 0 to 9, then that would be enough. Because 2 power 29 is less than, sorry, is greater than 10 power 8. 2 power 29 is greater than 10 power 8. And here this 10 power 8 information is mentioned in the constraint. The value of C is always less than or equals to 10 power 8. So it is enough to consider the first 29 bits, or I can say the first 30 bits. So let's say we have a binary representation of x like this, leading 0, then let's say we have 1, then again 1, then let's say we have a 0, 1, 0, and 1. Now let's say we have an integer a. This is my integer a, which will be given to you, and this is my integer b, right? And you have to find the minimum value of x. So I can say minimum value of x. Cool. So the very first thing, we always need to look at the bit of a c, this integer c. Can you explain again why 29 bits? Because 2 power 29 is greater than 10 power 8. So in integer c, we would not have more than 29 set bit. That's my claim. So if we consider the first 29 bits, then that would be enough. Because before it, every bit would be 0. So we don't need to worry about those bits. So we always need to look at the bit of a integer c. So at here we have 0, right? So what we are looking at this place. So definitely we are looking for 0, right? And 0 at here. And let's say initially these values are 0. So initially if these values are 0, and if you are going to make this a bit set, if you are going to make this bit set, then you would have a set bit in the result. So let me write the value also. So let me write the value of expression a XOR x, sorry, a or x, then and with a b or x. So if you make the bit set in integer x, then that gonna be set in this expression. So the result would not be equals to integer c. So we are not going to make this bit 1. So let's keep this bit 0 so that we would have a 0 at this place. Now coming to the next bit, again we have 0. So let's make all the bits 0 only. Now let's say for this bit in integer a we have a bit set, and in integer b, let's say we do not have a bit set, that is it is 0. So now what we are going to do, if at here you have a bit 1, and if at here you have a bit 0, and if you take a AND, then the result would be 0, right? But what we are looking for here, so we are looking for a set bit, because in integer c we have a bit set. So definitely we are looking to have a bit set, right? And the bit is set if and only if, in both the cases, if we have 1, because here we have AND operation. So 1 and 1 it is equals to 1. So in this expression we must have 1, and in this expression we also must have 1. So a contain 1 but b does not contain 1. So we are restricted to make this bit set in integer x, so that in both the places we would have 1, right? So I'm going to make this bit set. Cool. Now let's say we have 1 in both the places for the next bit. So if you already have a 1 at both the places, then we all know that in both the expression we would have 1. So If you make it 1, then you are going to maximize the value of x. But we are not interested to maximize the value of x. We are interested to minimize the value of x. So let's keep the bit 0 in integer x, right? Because the result is going to be 1. Because in integer a and in integer b, in both the integers we have 1, right? And let's say at these places we have 0, and instead of 0, let's say at these places we have 1. So at these places, let's say we have 1. So in that case, no matter whatever you have placed at here, the result would be always 1, right? And if the result is 1, then it is not equals to the bit in integer c. So in such case, we are going to simply return -1. That is, it is not possible to find any x. Any x does not exist. So this is one possible case when answer does not exist, right? So if we have any such case, then we immediately return -1. Now let's say we have an happy case at here, that is 0 at both the places. So we keep this bit a 0, and the result would be 0. Now let's say we have a 0 and 1. So we all know this expression would turn out to be 1, and this expression would turn out to be 0. And in order to make it 1, we are going to change the bit in integer x. So let's make a bit set in integer x. Now the result would be 1. And let me raise these to integer, because I guess now it is enough for the. Now you got an idea that how we are going to generate the minimum value of x. So let me summarize the entire algorithm. Iterate over the bits of x. If the bit is set, check for a and b. And in both the if a and b both has a set bit, then it's an happy case. We do not set a bit in integer x. And if any of the integer do not have a set bit, then we are going to set a bit in integer x. And if the bit in integer c is 0, then we are going to simply check if in both the cases the bit is set in integer a and in integer b, then it is not possible. Then valid x does not exist, so we simply return -1. Otherwise, they simply continue and check for the next bit. So this is the complete solution. It's a purely a greedy solution. Iterate from left to right. Now coming to the implementation. So initializing the value of x with 0. This is my answer. Iterate from 0 to 29. You can also iterate from 29 to 0. Totally up to you. This is my variable. If the bit is set, then it is 1. Then in integer a. And if the bit is set in integer b, then it is 1. Then similarly, we have a for integer c. If the bit is set, then this integer will be 1. And here I'm just simply checking if the bit is set in integer c, and if any of the integer do not have a set bit a or b, then we are going to make this bit a set in integer x. Otherwise, we simply check if both the integer has a bit set and we are looking for 0, then it is not possible. Valid x does not exist, so it simply return -1. The time complexity would be order of 30. The simply 30 iteration. So here Raj has asked, can we use a for loop from 0 to 10 power 8? But that solution would give you TLE, because we already have a better way. In 1 second, you can roughly perform around 10 power 8 iteration, but this value 10 power 8 is very close to the exact figure. So sometimes test cases are very tight, so that you cannot perform 10, exactly 10 power 8 iteration, and in some cases when the test cases are weak, you can perform 10 power 8 iteration. But just to be on the safer side, we always consider somewhere around 10 power 7. So write a quick plus one if it is clear to you. Now coming to the next problem, longest even length subsequence. So in this problem, you are given an integer array ARR and an integer k. Your task is to find the length of the longest subsequence of ARR such that the subsequence follow the given rule. The length of the subsequence should be even, and for the subsequence of length n, the maximum element this expression, which is nothing but the absolute value of a absolute difference of two adjacent element of the subsequence, must be less than or equals to k. And the best thing about this problem is a constraint. The size of the array can be up to 10 power 3 only. 3 into 10 power 3. So yes, we can write a solution with the time complexity n square that will pass all the possible test cases. So let's see how we can solve this problem. So the very first thing, length of the subsequence must be even. Then the second property that need to be satisfied, the maximum element between the absolute difference of any two adjacent element should be less than or equal to the given integer k. So let's say the first element of the subsequence is a sub of 0. This is the first element of the subsequence, and minus sub of 1 and their absolute difference. Then we need to take the next adjacent element of the subsequence. So sub of 2 minus a sub of 3 and so on. Basically the absolute difference between every adjacent pair of elements. And let's say the subsequence is having length m. So the last pair would be sub of m minus 2, the last second index, minus sub of m minus 1. And the length of the subsequence is even, so you don't need to worry about any case. And this value must be less than or equals to the given integer k, right? So this problem is based on a very standard problem of a dynamic programming, which is longest increasing subsequence. So just simply recall the recurrence relation of that problem. So we can easily solve with the help of our dynamic programming. So let's define a state dp of I will simply store the maximum length of the valid subsequence which is ending at index I. You can also say maximum even length of the valid subsequence. And this is very standard recurrence relation for the longest increasing subsequence problem. And the length of the array can be up to 3000. So that is one can write the solution with the quadratic time complexity n square. So we have fixed it, we simply fix index I, and now corresponding to index I, we are going to select the index j, and we are going to form a pair of I and j. So Rahul, what you can do, you can just simply try to write the recursion plus memorization solution by your own, and if you have any problem, then we can discuss in a comment box. So the first element of the array, it is a of 0 instead of arr, let's say a of 0. Then second element, a of 1, then a of 2, then a of j minus 1, some index j minus 1, then index j, then index j plus 1, then index I, then index I plus 1, and before index I we have index I minus 1, and up to index n minus 1. So we simply iterate over all the possible value for I. So run a for loop, simply run a for loop from I is equals to 0 till n minus 1. Right? So basically we simply fix index I, and then for index I am going to pair this index I with all the possible values of j. Right? So either you simply look in a right hand side, or you can look at in a left hand side. Both are valid. So let's say we decided to pair this with the index j which is on its left. So I'm going to simply pair these two integers, right? And when we can pair these two integers, so we can only pair these two integers if their absolute difference is less than or equals to k. So I iterate over all the possible values for j. So from 0 to j minus 1. 0 to I minus 1. Then they simply check if absolute value of absolute difference of a of I minus a of j, if it is less than or equals to k, then it is a valid pair. Yes, we can form a pair. Then what is the next information that we are looking for? The next information that we are looking for is the best possible value of the best dp value from the left hand side. So from here we are looking for the maximum value. So maximum value of any dp of x, right? And let's say we already have this information which is stored in index, which is stored in variable best. So let's say we already have this information which is stored in a variable which is named as best. So what will be my answer? So dp of I will be simply equals to 2 plus this variable best. 2 plus best. And best is nothing the value of a best, it is equals to the maximum value from the left hand side. So iterate over all the possible x from 0 to j minus 1 and a maximum value of a tp of x, right? And now if you try to implement in this way, then the time complexity would be n cube, and you will get a TLE. So what we can do, we can build this variable x in a progressive order, right? Because we are iterating from the smaller values of j to the bigger value of j. So before coming to the particular index j, we already traversed from 0 to j minus 1. So yes, we can keep track of a best dp value in a progressive order. So just simply declare the variable j at the top of a inner for loop, initialize this with 0, and before going to the next value of j, update this best, update this variable best. So best is equals to maximum of best that we have so far, comma dp of j. So in this way, you can solve this problem in n squared time. Now, what will be my final answer? The subsequence can end at any index. The subsequence can end at any index. So your answer will be equals to maximum value of dp of I. So from 0 to n minus 1, the maximum value of dp of I. This will be my answer. And the time complexity of this solution would be n square. So if there was something which is not clear to you, then what I would suggest, just go and try to solve the problem longest increasing subsequence of a dynamic programming. It is a very standard problem of a dynamic programming. And then again come to this problem and try to solve it by your own. The implementation is very straightforward. Taken the length of the array, then this is my answer. Then my dp array, initialize all the element with 0, iterate from 1 to n minus 1, the possible value of I, then for all the possible value of j from 0 to I minus 1, and if we can pair I and j, then update the value of dp of I, the maximum that I have so far, then plus 2 for the current pair I and j, and the best. Here the best is toward the best dp value from the left hand side, 0 to j minus 1, and update best every time. Then after this inner for loop, I simply update my answer. Instead of updating the answer here, you can also run another for loop and take the maximum value of dp of I. And recursion plus memorization will be an homework task for you. Try to implement it by your own, and you can just simply paste your solution in the comment box. We'll try to evaluate and we'll correct your solution. Otherwise, this session would become very lengthy, which I don't want. Rahul, you can post your 2D DP solution. We'll try to evaluate. So you are getting a memory limit exceed error. Now coming to the last problem of the contest, which was again an interesting problem. So minimum operations. In this problem, you are given an array of integers and an integer k, and you can shuffle this array. Additionally, you can perform the operation any number of times, and in each operation, you can select any integer and increment its value by k. and here you have to find the minimum number of operations that are required to rearrange the array into a palindromic subsequence, palindromic sequence. So the palindromic sequence that read the same backward as forward, and if it is impossible, then return -1. So for this first example, what you can do, you can apply the operation two times and make this element value equals to 5. Now this will be your resulting array, and it is a palindrome. Now this array is already a palindrome, so you don't have to perform any operation. Then the size of the array can be up to 10 power 5, basically a standard constraint. And these are the constraints for the value of k and the element of the array element. So let's see how we can solve this problem. And to solve this problem, you need to draw some observation. So this problem can be solved with the help of a hashing plus some greedy idea. Don't worry, we'll come to this very soon. So our final agenda is to make the array a palindrome, right? And we were allowed to shuffle the array, and we want to find the minimum number of operations. So the resulting array should be a palindrome, right? So let's say we have integer a of 0. Instead of arr, let's name the array as a. Then a of 1. Then a of 2. Then a of n minus 3. A of n minus 2. The last second index. And finally a of n minus 1. The last index, right? So these two values must be same. The first element of the array must be equals to the last element of the array, right? The basic property of a palindrome. Then second element of the array must be equals to the last second element. A1 must be equals to a of n minus 2. So what I can say here, the element which is at index I, it must be equals to the element which is at index n minus 1 minus I, right? So basically we are looking for a pair of element. So so this index I is only related with the index n minus 1 minus I. So every time we process a pair of elements, if we have two elements equal, then we place one element at index I and we place another element at index n minus 1 minus I. This is the basic property of a palindrome. Now coming to this problem. So in this problem, we were allowed to shuffle the array. So one can simply shuffle the array, that is, can consider any arrangement. Then we can perform operation, and in each operation, we can simply increment the value of any integer by k. So simply update a of I with a of I plus k, and this integer k will be given to you. So let me explain the problem with some example. So let's say we have integer array a, and its value is equals to 2, 9, 12, and let's say 14. So what I can do here, I can perform two operation on the first element and make it equals to 12. Then I can perform one operation on the second element, and basically let's say the value of k, it is equals to 5. So perform two operation on the first element and one operation on the second element. So then this second element would be equals to the 14, and this first element would be equals to 12, right? So this will be my resulting array. and basically it is equals to 12, 14, then 12, and again 14. Now after this, we can just simply shuffle this array and change this array into 12, 14, 14, and 12. Now it is a palindromic array, or I can say palindromic sequence. Now here we can draw one observation, which is the most important observation to solve this problem. So what is the observation here? If you have noticed one thing, then the value of a 2 mod k, it is equals to 12 mod k. In both the cases, the remainder is 2, right? Both has the same remainder. And the 9 mod k, it is equals to 14 mod k. This is the most important observation to solve this problem. And try to pay more attention, just to mark my words. We can make the elements equal if they have the same remainder, right? So we are going to process the element, all the elements together, which has the same remainder. So let me write this thing here. And two elements whose remainder are not same are not related with each other anyhow. You can never make the elements equal if their remainders are not same. So for example, let's say the value of k, again it is equals to 5, and let's say we have an array with the element 7, 22, then let's say we have a 4, then 42, then let's say we have a 117, and let's say that we have a 24. Now if you have noticed one thing, then integer 7, integer 22, integer 42, and integer 117. All these four integers has the same remainder, which is equals to 2, for a value of k is equals to 5. Then integer 4 and integer 24, they both has the same remainder. So I can make these two integers equal. The integer which are colored with the red is not related with the integer which are colored with the blue. You can never make the integers equal. So that's why we are going to process the element with the same remainder, right? So now let's let's do some casework. And for this thing, just simply declare a map with the value vector, or I can say map with the value list. So the key will store the remainder, and the corresponding list will store the integer which has the which has the following remainder. So case 1, when the length of the sequence is even. So let's say the length is even. So in that case, what will be my answer? So let's say you have integer 7. Then let's say we have a 42. Then let's say 117, and let's say 22. So the very first thing, Now I'm going to sort this array. We'll come to this we'll come to this very soon, that why it is necessary to sort this array, because we want to minimize the number of operations. So 7, then 22, then 42, and 117. So in order to minimize the number of operations, I'm going to make these two adjacent element equal. And this is my greedy idea. This is the perfect greedy idea to minimize the number of operations. And I'm going to make these two adjacent element equal. If you consider any other configuration, then you are basically maximizing the number of operations. Here the value of k, it is equals to 5. The value of k, it is equals to 5. So just simply perform 3 operations on the first element, right, and few operation on the third element to make it equals to 170. And exactly how many operations do we require to perform? That is my answer. Will be equals to 22 divided by 5, and take its floor value, minus 7 divided by 5. These many operations you require to perform to make the first two adjacent element equal. Then to make the second two adjacent element equal, the number of operations that I required, it is equals to 117 divided by k, and take the floor value, minus 42 divided by k, and take the floor value. These many operations you require to perform to make both the adjacent element equal, and then we shuffle accordingly at the end. That is, place one element at index I, then another element at index n minus 1 minus I. So this is very straightforward, and this is the best strategy to minimize the number of operations. But what if we have odd length? So let's say case 2. So it is very obvious that we are going to sort this array of element which has the same remainder. So let's say when we have odd length. So let's say we have integer 7, then integer 22, then let's say integer 42, and then let's say we have what I can say, let's say 102, and let's say then 117. Now if you have noticed one thing, definitely we are going to short this array, and actually it is already shorted. So now if you are going to pair these two adjacent element and these two adjacent element, and if you are going to make this element as a center of a symmetry, because it might be possible when the array has a odd length. For example, let's say we have a 5, 2, then here I can say, let's say we have 8, then 2, and then 5. So at these places we must have the same element at these places. Now here we have one element which is a center of a symmetry. Now this element could be anything, and I don't have to satisfy any property. This element could be anything. I don't have to satisfy any property. So I'm calling such element as a center of symmetry. So this 117 can be my center of symmetry, right? But tell me one thing: is it the best to have 117 as the center of symmetry? No, this is not the best. So basically what I'm trying to say, when the length of the array is odd, we have a multiple possibility for the center of symmetry. We can't claim anything. It might be possible when the element 42 is best for the center of symmetry. It might be possible when the element 7 is best for the center of symmetry. Right? So we have to check for all such cases. Right? So I can write it here. Possibilities for center of symmetry. So this will be my completely a greedy idea. So the first possibility is the last element of the array. This will be my center of symmetry. And then I'm going to, if this is my center of symmetry, then what are the possible pair? This is my first adjacent element, and then this would be my second adjacent element. In this case, the center of symmetry is 117, right? But we all know it is not the best one. So the second potential value that could be a center of symmetry is 102. But I can claim this thing very easily that it is never possible to have this array, this 102 as a center of symmetry. Because if you are going to consider 102 as the center of a symmetry, then you are going to pair these two elements. So instead of pairing these two elements, it is always better to pair these two elements and keep 117 as the center of symmetry. Or it is always better to pair 102 and 117 as a center of symmetry. So such possible cases are not there. So the potential value for the center of symmetry is 117. Then in that case, we just simply pair these two elements and these two elements. That is, we make these two elements equal, right? The other potential value would be 42. So if I consider 42 as the center of symmetry, then this will be my first pair, and in this pair I will make both the elements equal. This will be my second pair, and I will make both the elements equal, right? Then another potential value for the center of symmetry, it is 7. It is 7. So then this will be my first pair, will make both the values equal, and the second pair 102 and 117, and will make both the values equal. So in case of a even length, we can easily find the answer, but in case of a odd length, we have some other possibility for the center of symmetry. Now let me just simply generalize this idea. So just simply iterate over the entire array and declare a map where the key will be the remainder, and corresponding to every remainder, we have the set of integer. We have a set of integer, right? And if for a particular remainder, if the corresponding list is having even length, then we can easily find the answer. And in case, let's say the length is odd, then what happened in that case? So the very first thing, corresponding to every remainder, we have a list of integer. Let's say this list is named as a B. It is same as my implementation. Array of integers with same remainder. Cool. So let's say its length is odd, and let's say its length is 5. So the first element, b of 0, then a b of 1, then a b of 2, b of 3, and a b of 4. So first I'm going to pair these two integers, then I'm going to pair these two integers, and I have considered this b of 4 as the center of symmetry. So in that case, what will be my answer? What will be my current answer? It is simply equals to b of 1 divided by k minus b of 0 divided by k, right? And plus b of 3 divided by k minus b of 2 divided by k. So here I have considered b of 4 as the center of symmetry, right? But it might be possible when the b of 2 is the best center of symmetry, or b of 0 is the best center of symmetry. So in order to find all the possible value for the center of symmetry, let's iterate from m minus 2. Here m is the length of array b, which is sorted. So do not get confused. This array b is a sorted, and if it is not, then we are simply going to sort this array b. So iterate from m minus 2, that is the last second index, and up to 1, up to index 1, right? And initially I'm going to store this value. And one very important thing, if you have noticed one thing, from each term we have to divide it by k, right? So in my implementation, what I did, I initially divide each integer by k. So let me show you implementation side by side. So this is taken the length of the array, then declared a map. The key will be remainder, and the value will be a vector which has this remainder. I iterate over all the integer. Then this is my remainder, and corresponding to the list, I'm going to simply add the value ARR of I divided by k. So instead of dividing it by k later, I'm going to divide it by k at here only, right? So I don't need to bothered about this operation. So I can just simply remove this. So let me write it in this way. And another integer, center of a symmetry. So as per the discussion, I already told you what are the potential value for the center of symmetry. They are b of 4, b of 2, and b of 0. These are the potential value for the center of symmetry. Any other value cannot be the center of symmetry. We can easily prove by just without knowing the values. We can easily prove only these are the possible value for the center of symmetry. So I'm going to initialize my variable current, which is store the current answer, the current minimum number of operation which we are required, and it is b1 minus b of 0. Again, I'm going to repeat this thing. This array b is sorted. Then b of 4 minus b of 3, right? So basically, simply pair first two element and then the second two element. So I have considered this b of 4 as the center of symmetry. Now I need to consider b of 2 as the center of symmetry. So for this thing, I can run a loop. You might have some different implementation, but here I'm going to explain how I implemented this thing. So from m minus 2, that is from index 3, to index 1, and every time we are going to take a jump of 2. So while the value of I is greater than 0 and I is equals to I minus 2, every time I'm going to update in this way. So starting with the index 3, then we are going to take a jump for index 1, right? And here what I can say, so basically first how I'm going to find this value, let me write the for loop for this also. So I iterate from I is equals to 1, while the value of I is less than m and I is equals to I plus 2. So in your variable current, which is initialized with 0, just simply add this value b of I minus b of I minus 1. Just simply add this value in your variable current. So for the first pair, b of 1 minus b of 0, then b of 3 minus b of 2. So b of 3 minus b of 2, right? and then iterate from this index 3. And since I simply added p of I minus b of 1, so now this time what I'm going to do, I'm going to subtract this pair. So minus equals to, or I can just simply write in this way. So current plus equals to b of I minus b of I minus 1. So just simply subtract what you have added corresponding to this pair, and now I'm going to pair this b of 3 with b of 4. So basically this is what I did previously. This is what I did previously. So now I'm going to subtract this thing. Now I'm going to simply subtract this thing, and now I'm going to consider this one, b of 3 and b of 4. So plus, so current minus equals to this expression, and current plus equals to b of I plus 1 minus b of I. Now if you simplify this equation, then this can also be written in this way. So current plus equals to b of I minus 1 plus b of I plus 1 and minus 2 into b of I. So in this way, we can consider all the possible potential value for the center of a symmetry. And next time, take a jump of 2 and consider this pair. Just simply remove this pair. Just simply remove this pair and consider the pair b of 1 and b of 2. So in this way, we can solve the problem for odd length. Right? The overall time complexity would be n log of n base 2 because I have used a hash map. Now coming to the implementation, taken the length of the array, iterate over all the integer corresponding to every remainder, just simply add this value in a list AR of I divided by k, then initializing the answer with 0. Iterate over all the remainders, and this is my corresponding set of integer for the particular remainder. Then sort this array B, initializing the current answer with 0, and I'm going to simply count how many lists we have which has the odd length. And if we have a more than one list which has the odd length, then the palindromic array is not possible at the end, because in my final array we can only have a one element as the center of symmetry. So that's why if we have more than one list which has the odd length, then simply return -1. Cool. Then this is my current value and initializing best with the current, and if the length is odd, then we have a multiple values as the center of symmetry. Iterate over all the potential values and update the variable current, and simply take the best out of all the possibility. So yeah, these were the solution for all the 4 problem of the last weekly contest. Hope you have learned something new, and make sure to write your feedback in the comment box so that we can improve the upcoming problem set and upcoming analysis. So thank you everyone for joining this live stream or watching this recording. So yeah, bye bye, and have a good day, good night.